All right. I think I said part two, but this might even be part three. I'm lost. Either way, let's continue on with chapter 9. Um, how is PZT created? The characteristics of PZT doesn't just happen spontaneously. We have to make this material have those characteristics, all right, to be able to do the things that it does, changing electrical into sound and sound into electrical energy. How do we do that? By polarization. We expose the material to a strong electrical field while being heated to a substantial temperature. So we put it in this big electrical field, at the same time heat it to a super high temperature. The temperature at PZT, or the temperature at which PZT is polarized, is called the Curie temperature or Curie point. In other words, we heat and heat and heat, and the second that polarization occurs, that temperature at which that polarization occurs is the Curie temperature or the Curie point. Now, it's important to understand, if the polarized PZT is heated above that temperature, 1 degree above that temperature, the crystal's piezoelectric properties are destroyed. So we make it with heat, but we can't heat it any higher than absolutely necessary to make that, to give it those characteristics. But if we go any higher than that, past that Curie point or Curie temperature, we immediately destroy those piezoelectric properties, or its ability to turn sound into electrical or electrical into sound. All right? This is called depolarization. The PZT is said to be depolarized. So we polarize it, or polarization is that heating it up to that point that to give it that properties. But anything above that, if it's heated above that Curie point or Curie temperature, we depolarize it or destroy it. So here's some extra info. Sterilization, okay? We're going to talk about cleaning these probes. Sterilization is the destruction of all microorganisms by exposure to extreme heat, chemical agents, or radiation. They do this in surgery a lot with all those reusable tools. They clean them, then they sterilize them, okay? Disinfect. Now, the sterilization is by extreme heat. All microorganisms are destroyed with sterilization. Why? Because it uses extreme heat. Disinfection is the application of a chemical agent to reduce or eliminate infectious microorganisms on an object. Something called Sidex, or there's germicides that do this. It's a spray-on application. This is what Annette is doing to her countertops. She's not sterilizing them because she doesn't have a flamethrower and heating up her granite countertops. She's taking her Clorox wipes and disinfecting the countertops or the granite countertops by she's killing most of them, okay? She uses that chemical agent to reduce or eliminate infectious organisms on an object. Now, Annette, your countertops are clean enough. I'm not telling you to go out and buy a flamethrower and sterilize your countertops with heat. What you're doing is fine enough. Keep up the good work. I love you. So which one should we use to clean the ultrasound probes? Of course, disinfection. Why? We just learned that if we heat these probes up too high, we actually destroy them or destroy the properties that they have, that we want them to have for ultrasound. We use disinfection on ultrasound probes or germicides or spray-on applications to prevent depolarization and damage to the probe. Another thing that would happen is the probe would melt under those temperatures because they're made out of plastic. The case is plastic, rubber and plastic. So only instruments that penetrate the skin or mucous membranes require sterilization. You know, those are the scalpels and the clamps that go inside the body. Things that touch or penetrate inside the body. Those require sterilization. Most of those are metal objects anyway. So now that we know all the parts and how to clean the transducers, what determines the frequency of sound produced by a transducer? So we learn how they're made. We learn PZT crystals. We learn parts of it. We learn all this good stuff. We want to know now, taking it a step further, what determines the frequency of sound produced by a transducer. So let's first introduce briefly the two types of transducers. Remember, we learned this a second ago, earlier in Chapter 9. There are continuous wave transducers, and there are pulsed wave transducers. And we talked about that continuous wave versus that pulse wave, even as far as, like, I think Chapter 2 introduced that. So continuous wave transducers. Continuous wave. It's always on. There's no off time, right? It's that simple. Produces an electrical signal that excites the active element. The frequency of sound is equal to the frequency of the electrical signal. The electrical frequency equals the acoustic frequency. And on page 126 at the bottom of the page, and let me turn to that for you guys, it gives you an example. The transmitter of a continuous wave ultrasound system creates an electrical signal that continuously excites the PZT. The electrical signal has a frequency of 6 megahertz. So, if the electrical frequency is 6 megahertz, what's the acoustical frequency? Well, therefore, continuous wave sound created by the probe has a frequency of 6 megahertz. It's that simple of a principle. It's a continuous thing. So whatever that electrical frequency is, that's what the acoustical frequency is. So pulsed wave transducers. Pulsed wave, that's simple. There's an on and off time. That's what we use in ultrasound. That's what creates images, correct? Produce a short duration electrical spike that travels through the wire and strikes the PZT crystal in the transducer. In other words, it's not a continuous electrical current. It's just a quick little electrical spike that travels through the wire, hits the transducer, and that creates a frequency sound. Frequency of sound created by the active element depends on the characteristics of the active element in the transducer. So it's no longer determined by that electrical spike. It's determined by the crystal. That frequency of sound is dependent on the characteristics of the active element in the transducer. Those characteristics, there's two characteristics of the active element that combine, that combine to determine the frequency of sound from a pulsed wave transducer. Those are the speed of sound in the PZT and the thickness of the PZT. These are simple, straightforward relationship principles that we're going to talk about, okay? So number one, the speed of sound in PZT. The speed of sound and frequency that is created are directly related. So in other words, if that PZT has a real fast or faster speed of sound, then that frequency is going to be higher. If the speed of sound in a particular PZT element is slower, then when that electrical current hits it, that short spike hits it, the frequency is going to be lower. Again, this is one of the characteristics of the PZT that determines the frequency of that sound beam, because we have a short electrical spike, right? So when that short electrical spike hits it, if that PZT has a fast, or the speed of sound that PZT is faster, frequency is higher. You see the relationship, directly related. If the speed of sound in that PZT is lower when that electrical spike hits it, slower, the frequency is lower. Very simple principle. You just have to kind of commit to it and remember it. So it's a relationship issue. If you understand the relationship, you can answer the questions. So let's talk about the thickness of the PZT. How does that affect the frequency that is produced, or the frequency of sound that is produced when that electrical current hits it? The thickness and frequency are inversely related. All right? If you have a thinner element or thinner crystal, okay, thinner, you have a higher frequency. If you have a thicker element or thicker element, you have a lower frequency. Let's think about it. You know, if I have a big block of wood, a big thick block of wood, and I knock on it, you're going to hear that dull thud or that low thud. Versus if I have a real thin piece of wood and I knock on it, it's going to have that higher pitch or that higher frequency. It only makes sense. Think about it that way. So, the rule to know is the thickness of the PZT crystal in a pulsed wave transducer is equal to half of the wavelength of the sound in the PZT. You already know that. We learned it two videos ago. The thickness of the PZT crystal in a pulsed wave transducer is equal to 1/2 of the wavelength of the sound in the PZT. That's the rule to follow. Thank you, Jesus. Let's eat. Of course, we were supposed to finish this in class, but we didn't. So, grasp these principles again. You know, do what you have to do to understand them. Break it up into pieces. It's very straightforward and simple. When we get to class Monday, we're going to break all this down again, and we're going to go over everything again and make sure you understand that so that you're prepared for the test Tuesday. But use these videos. Hopefully they'll help. Please give me some feedback if you like them, if you don't like them, what you would like to see different. You know, I'm going to try to improve them as much as I can, and we'll take it from there. So, peace out, and I'll see you Monday.